Hello and welcome to this recorded e-learning on synthesis options. My name is Frank Nelson. I'll be your instructor for this module. This module introduces many of the synthesis options that are available in the latest FPGA synthesis tools, including Xilinx's own XST. This module introduces the primary synthesis options and the concepts behind their usage. These synthesis options can have significant impact on the quality of results a designer will get when synthesizing for an FPGA. This module also provides some detailed introduction to the specific options included with XST. These synthesis options will impact the speed of your design and help you manage your FPGA resources. If you are an experienced ASIC designer or new to FPGA design, this module will help you use your synthesis tool to full advantage. This module will help you reduce your learning curve and get productive faster with your new FPGA design. This module will help you build an efficient design that will use minimal FPGA resources and get good performance. These practices are designed to promote fast and efficient FPGA designs. After completing this module, you should be able to identify synthesis tool options that can be used to increase performance and/or reduce your design size. You should also be able to describe an approach to using your synthesis tool to obtain higher performance and gain time enclosure. And you should be able to find these options as part of the XST software so you can get the most out of your HDL. The guidelines in this module are not specific to any particular synthesis tool or Xilinx FPGA family. However, at the end of this module, I will discuss the XST synthesis options and show you how to find them. The options we're going to discuss will provide support for all of Xilinx's FPGAs. This flowchart is used extensively as part of our Designing for Performance course. And in that course, our primary objective is to show designers how to meet all of their timing needs. In this diagram, the first 4 steps in the upper left-hand corner describe the high-level procedures that all designers must follow early in the design process. These include making good pin assignments, understanding what a reasonable timing objective is, build their HDL code so they can get the optimum FPGA resources in their design, and making good timing constraints to be used during synthesis and implementation. Step 5 is to choose a synthesis strategy and goal. We will talk about what that means a little later, but for now you should understand that this choice will direct XST to synthesize your design in a pre-optimized fashion using recommended synthesis options. This makes it easy for a Xilinx designer to get their design synthesized easily. However, most experienced designers would rather go ahead and have the knowledge to customize the options as they choose. So we're about to go into that in this module. Now, step 6 is to synthesize the design. After synthesis, most designers are evaluating the HDL code associated with their timing critical paths. This is very smart. As you'll learn, your HDL coding style has perhaps the largest impact on the speed and the size of your design. So the smartest designers are busy isolating their timing critical paths, that is, those paths that fail to meet their timing constraints, with their schematic viewer and then verify that their HDL is optimal. Now this might require the designer to add a pipeline stage, recode some components, or instantiate an appropriate component that their synthesis tool is not inferring. All of these design changes can now be made before a single implementation, that is a place and route, has been completed, and that saves our customers a great deal of development time. After fixing the design, most customers should consider using their synthesis tool to full advantage, and that's what we're about to go into. And after resynthesizing with different options, perhaps even synthesizing multiple times with different settings, most designers then complete their first implementation. So keep in mind that using just a single set of synthesis options may not be sufficient. After reviewing this module, you should be able to anticipate which of the provided synthesis options might work best for your design. And of course, your results may vary because every design is different. But after synthesizing, optimizing your HDL, and instantiating the necessary resources, it is our intention that you should not have to go back to the design stage and resynthesize again. Many new customers are disappointed that they're going to have to instantiate some of the most popular FPGA resources into their design and that their synthesis tool won't infer everything they want. Well, this is now pretty much standard operating procedure in the FPGA industry, and what I mean by that is that most customers are prepared to create highly optimized cores with the Xilinx core generator or the architecture wizard utilities, and then instantiate those components into their HDL. This flow allows users to work around the limitations all synthesis tools have with regards to automatically inferring the best FPGA resources. The bottom line is that all of the high-end synthesis tools available for the FPGA industry usually do not allow inference of all of the best FPGA resources. Usually the latest and greatest will allow some inference support of the DSP slice and block RAM. Now, synthesis tools may allow some inference of these resources. There are plenty of exceptions, however, but usually only primary applications are inferable. For example, the block RAM resources are inferable for memories that only use a single block RAM or are not initialized and don't use the output register. Simply put, it is too difficult for synthesis vendors to keep up with all the possible configurations of a single FPGA resource and build the ability for users to infer all possible functionality. To aid customers in building a desired component of complete functionality, Xilinx recommends that users build these components with the core generator architecture wizard. And when I mention high-end synthesis tools, I'm referring to the most popular synthesis tools available for the FPGA industry, specifically Simplify, as well as Xilinx's own XST. While this module is not about how to instantiate the best resources, it is an important skill to be able to do so. Xilinx provides some basic information about instantiation of these device resources in the Synthesis and Simulation Design Guide. This document can be found in the standard ISE software documentation or at support.xilinx.com. The next step is to achieve breakthrough performance is to write the best HDL code possible for your design. To help you write better code, we provide 2 basic HDL coding RELs and 2 Spartan 6 and Vertex 6 HDL coding techniques RELs. All are free and available at the same location you found this recorded e-learning. So if you've not seen them, check them out. The last step is to drive your synthesis tool and the implementation tools to the best of your ability. Well, we'll discuss the proper use of the implementation tools in the Essentials of FPGA Design course and the Designing for Performance courses as well. But this module is going to try and teach you how to use your synthesis tool to full advantage. To get optimum speed, device utilization, and minimal power consumption, customers need to plan on targeting as much of the FPGA's dedicated hardware resources as possible. This means that users not only have to plan on instantiating the proper resources, but sometimes have to look for creative ways in which to use those dedicated resources. For example, most customers would think to build a FIFO with a block RAM, but most would not consider building a finite state machine with a block RAM. Very often, customers choose a device that has some dedicated resources left over. So to get the most out of the FPGA, users have to very often pack the most into the FPGA. The reason these resources are so fast is because they have a fixed structure and are not built with LUTs and registers. They provide as much as 3 times the speed and use the dedicated hardware resources to full advantage, which will save you LUTs and registers for other functionality you can build into the FPGA. This slide is trying to highlight some of the benefits of using good HDL coding techniques. Not only do users have to be aware that not all FPGA resources are easily inferable and that they have to make sure they are getting the best resources, but designers have to be able to find their timing critical paths and then recode. This is usually done by designers adding timing constraints during synthesis and then finding those paths with their schematic viewer. Likewise, while building their design, most customers know that they should use synchronous sets and resets and how to add pipeline stages. But in general, users have to think about the number of levels of logic they infer and the negative impact those extra levels of logic can have on the speed of the design. To help with this, we want to encourage you to listen to those RELs I already mentioned about basic HDL coding. These are the primary synthesis options designers are using to improve their system speed. We're going to talk about each one of these features in detail. They include timing-driven synthesis, finite state machine extraction, retiming, register duplication, hierarchy management, resource sharing, and physical optimization. These options can greatly impact your design speed and device utilization. which we commonly will call the area of the design.